Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tare, and this is my ninth video on my sub-series of integration on my series of first year calculus. And today, I think it's going to be a pretty short video. I'm just going to talk about how to evaluate these four additional elementary integrals. These are probably ones that we should have done before, but you'll see how to derive them. I'm going to show you how to derive each of these integrals. These are very useful. So anyway, let's begin. Here's just an enlarged slide showing you the values of these integrals. These are the four additional integrals of the basic trig functions. We already know how to integrate sine and cosine. Those are very easy. But these are trickier, and I'm going to show you how to do them. The first two aren't that bad. The last two, you have to apply a very unobvious trick, which I'll show you later. But anyway, what do we need to do? This rule is useful for all four of these integrals, it turns out. And this is a little bit of a joke. I call this the log cabin integration rule. It's a good mnemonic. It's kind of funny, and it's a good way to remember this rule. So suppose we have any quantity which we call cabin, and cabin can be anything. It can be anything that depends on several variables or maybe just one variable, whatever. But it has to depend on at least one variable. And if that's the case, then if you're integrating, if you take the integral of d cabin over cabin, you get log, this should really be ln, but ln, sometimes people write ln as log, actually. There's no good reason we still use log for base 10 logs. It's a little bit archaic. And as a matter of fact, when you get into kind of advanced math, sometimes people don't even bother writing ln anymore. They just write log, and it's always understood that they mean the natural log. So anyway, the rule is the integral of d cabin over cabin equals log. And yeah, it's a little tricky. You have to use an absolute value in general because you don't know that cabin's necessarily positive. Could be negative if it's a real value quantity. So it's log of absolute value of cabin plus c. Just log cabin. That's pretty easy to remember. And really, there's a couple things you have to remember. First of all, the absolute, and also, like I said, that by log, it really mean ln. So anyway, that's the rule, and I think it's pretty easy to remember. So let's apply that rule. We can apply that rule to integrating the tangent and the cotangent. And they're very similar. I mean, whenever you have co-functions, trig functions, sine and cosine, they behave very similarly to each other in terms of differentiation and integration. Let's just look at the tangent first. That's the part on the left. So the integral of tangent, and you probably remember from basic trig that tangent can also be written as sine over cosine. So this is really just the integral of sine x over cosine x dx. But d of cosine is nothing but minus sine x dx, if you like. So we put a minus sign outside the whole integral, and now we have d cosine x over cosine x. Well, now this is the form d cabin over cabin. Cabin is now cosine x. So we know the answer is log cabin. In this case, cabin is cosine x, and we have to remember to put an absolute value around it. We also have to remember that it's negative because the whole integral is negative. And we always get an integration constant at the end. And if you like, you can even simplify this further. Sometimes people are happy writing this form minus log cosine x plus c, but we can actually write it another way. And the way we do that, you notice that the negative log of anything is just the log of the reciprocal of that thing. So minus log of cosine x is the same as plus log of 1 over cosine x, just because of the property of natural logarithm or any kind of logarithm. And now you probably remember that 1 over cosine x can also be written as secant of x. So you can also write the answer as log of absolute value of secant x plus c. It's the same thing. Sometimes people prefer to write it this way. But you can write it in either of these two ways. Minus log cosine plus c or plus log secant plus c. And the integral of cotangent is very similar, same idea. Cotangent is cosine over sine. This time we don't have to worry about any minus signs because cosine is already the derivative of sine, so it's just d sine x over sine x. Again, we can apply the log cabin rule. If we let cabin be sine x here, we have d cabin over cabin, integral that, and that's just log of absolute value of cabin, which in this case is sine x, plus c. Voila. So those are pretty easy, just using the log cabin. But secant and cosecants are a lot trickier. And somebody figured out this trick a long time ago. I don't know who it was. It's not an obvious trick at all. But let's just look at the integral on the left, the integral of secant x dx. And by the way, there are more straightforward ways to do these integrals. But let's just do it this way for now. The important thing is just getting the result and seeing that it works. So here's why we integrate secant. You might wonder whoever thought of this. But what we do is the trick we use is you can always multiply anything by 1. You can always multiply it by any quantity, no matter how complicated it looks, as long as that quantity is equal to 1. And you know that any ratio, any fraction where you have the same numerator and denominator is equal to 1. So let's write this funny fraction here. Fraction of secant x plus tangent x over secant x plus tangent x. This is 1, so we can always insert that in there. Let's just see what happens when we do that. Now we can multiply secant x by the numerator, and if you do that, you get secant squared x plus secant x tangent x. And in the denominator, you have secant x plus tangent x. And now you might have noticed something interesting here. Secant squared x is just a derivative of tangent. And similarly, secant x times tangent x is the derivative of secant. So the numerator is really just the derivative of the denominator. Who would have thought? But this works. It works kind of miraculously. So now we have d of secant x plus tan x in the numerator. Remember, derivative's linear, so we can combine them. And then we have secant x plus tangent x in the denominator. Again, we can apply the log cabin rule. We have cabin here is secant x plus tangent x, so we have the integral of d cabin over cabin. We know that that's log of absolute value of cabin, ln of absolute value of cabin, plus c. In this case, cabin is secant x plus tangent x. So we're left with ln of absolute value of secant x plus tangent x plus c. That's how you integrate secant x. And you can integrate cosecant basically the same way. This is the cofunction of secant. I don't know if I'm going to go through all the steps. Yeah, oh, I forgot a minus sign here. Yeah, this one does have a minus sign. There should be a minus sign on the last two lines on the right. The actual result for the integral of cosecant is minus natural log of cosecant x plus cotangent x plus c, because I forgot that the integral of cotangent is merely minus cosecant squared, and the integral of the derivative of cosecant is minus cosecant x cotangent x. So sorry about that. There should be minus signs there, but you get the idea. So that's how you get those two integrals. And so that's really all I wanted to do today. But now we have this nice table of integrals. This is kind of a nice starting table of integrals. Whenever you're doing integration, it's always really useful to have a table of integrals in front of you. Because, it's hard to memorize all these integrals for one thing. It's kind of hard to derive most of them, off the bat. It's better just to have a table in front of you. Then you can solve a lot more complicated integrals using, some other integration tricks, including substitution and integration by parts. There's actually a third trick I'm going to teach you, maybe starting the next video. There's another third trick called integration by partial fractions. That's a really useful rule when you want to integrate rational functions. But I'll get into that later. Anyway, we know how to do all these integrals now, except the only ones we haven't gone over are the last two, 19 and 20. There's a couple ways you can do this. We actually have all the machinery we need right now to do 19 and 20. You know, I think the easiest way is to use what's called hyperbolic functions, which are the kind of analogous to trigonometric functions. I don't know if you guys have learned about hyperbolic functions. They're pretty simple. Maybe I'll do that next. First, I have to tell you what the hyperbolic functions are. They're written with an H. And they're analogs of all the ordinary trig functions. There's sinh, S-I-N-H of x. There's cosh, C-O-S-H of x. You can express them all in terms of e to the x, it turns out, and e to the minus x. And then there's the inverses of those functions, and you can write those in terms of natural logs. And those are very useful functions. So maybe I should do that next, and that'll give us 19 and 20. And then we'll have this nice table, and then we'll be able to do, pretty much any kind of integral we want. But anyway, that concludes my video for today. Thank you for watching. Long live math, and I'll see you guys next time.